In this video, we're going to extend our knowledge of graph theory and the consensus equation to do cool things besides have robots agree on a location to have a massive collision. We're doing consensus, but at the end of the day, robots driving towards each other is just a disaster waiting to happen. So let's do something cooler, like have robots chase each other in a circle, or hold geometric formations, using the same framework that we've been developing. Let's get started. In the previous video, we talked about information sharing, how robots actually transmit information between each other, what this information could be, and most importantly, how we represent it mathematically using graph theory. So far, what we've done with this is talk about the consensus equation and really formalize how we have robots using only local information meet up with each other at a location if we have collision avoidance enabled, or slam into each other if we don't. We've discussed how the graph topology will change the behavior of the robots, how which robots looking or getting information from which other robots will ultimately change the behavior of the rendezvous equation. Whether you have a Gabriel graph or a delta disk graph, what happens at the end of the day will be fundamentally different. Now, let's look at a slightly different graph topology and augment our consensus equation so that the robots do something a little different, where they're going to actually just chase each other in a circle rather than drive towards each other in order to meet up at a location. So our goal is now to perform cyclic pursuit, which is shown here in the simulation on the right, where 6 robots are chasing each other along a circle of constant radius, represented by the red line here. We'd also like to do this using the methodologies that we've been talking about in previous videos, so graph theory and more particularly the consensus equation. But if we use the graph topology shown here by the blue lines connecting the robots, and the edges are undirected like we've been used to, well, these robots are going to drive towards each other. So in order to make them chase each other like this, what we want to do is have a directed topology, or a directed cyclic graph, like the one shown on the right here, where we have robots as vertices as usual, but our edges that connect robots into one another or represent information flow to one another now have an arrow associated with them. So in this case, robot 1 is passing information to robot 2. Or in the consensus case where we're measuring distances, robot 2 is able to measure and care about robot 1's position. So if we're running consensus, robot 2 will run towards robot 1, but won't care about robot 3. Robot 3 will care about robot 2, and thus will chase it and try to follow it. And now let's take a step back to the whiteboard, see how directed graphs are different than undirected graphs in terms of graph theory, and actually start moving towards applying this cyclic graph to our consensus equation and see what happens. Before we dive into cyclic pursuit, let's figure out how we should handle this new graph topology and what the difference is between an undirected graph and a directed graph. And most importantly, how we develop the graph Laplacian that seemed so nice in our previous videos for this directed graph scenario. So let's consider a simple scenario. We have 2 robots, robot 1 and robot 2. And previously, we would put an edge between them, meaning they could share information back and forth. And this was our undirected edge. Now in cyclic pursuit, we are going to no longer have robots sharing information back and forth in an undirected channel. We're now going to say, okay, robot 2 doesn't care about robot 1. If we're going to run consensus, it's going to sit still. It doesn't want to move at all, and robot 1's going to have to do all of the work. So that means that, well, robot 2 doesn't care, so the information share is only now one directional. So robot 1 is receiving information from robot 2. So robot 1 is measuring robot 2's position for the consensus equation, and so the information flow represented by this arrow goes from 2 to 1. The information about robot 2's state, where it's living, is going, or where it's positioned, is pushing into robot 1. So let's see how this comes out with the consensus equation. So recall the consensus equation where we have x dot of I, so how the ith robot moves is the sum over its neighbors of its neighbor position minus its position. And this will drive us all on top of each other, everyone moving towards everyone else that they can see within their neighborhood. So how is this going to work for our case? Well, x1 is not really changed. x1 dot, the neighborhood where they're getting information from, is still x2, so this is just going to be x2 minus x1. x1 is going to behave exactly the same as if we were running standard consensus with an undirected edge. And it will just drive towards robot 2. But robot 2, well, it's not going to move. There's no information going to it. It's not measuring robot 1's position, and since there are no neighbors here, well, it's not going to do anything, which makes sense. If it doesn't care about robot 1 and we're running consensus, its job is to sit still. So how does this translate into the graph Laplacian? Well, recall that the graph Laplacian is the degree matrix minus the adjacency matrix. And the reason that we care about this so much is this consensus equation here can be written as x dot equals minus Lx, where L is our graph Laplacian. But now this degree matrix there's two options here now with directed edges. We can choose the degree of edges that end at a certain vertex, or the number of edges that begin at a certain vertex. These are called the in-degree and the out-degree matrices, respectively. Now, we really care about where information is going to, so the in-degree matrix, because information going to a unit will influence how its dynamics behave. So we're going to change how the Laplacian goes for our directed edge case, for our cyclic pursuit case, to be d in minus a. And so let's write out these matrices. D in is going to be, well, for robot 1, there is one edge that ends at it, so there's going to be a nice 1 here. There's no off-diagonals elements. And for robot 2, well, there's no edges that go into it. There's no information going into robot 2, so it's going to have a 0 here. For our adjacency matrix, recall the adjacency matrix cares about where information is going from and where it's going to. So we can think of this as where it's going to and where it's coming from. So to either robot 1 or 2, and coming from either robot 1 or 2. There are no self loops, so there's no information going from robot 1 to robot 1. There's also no information going from robot 2 to robot 2. There is information coming from robot 2 to robot 1, so there's going to be a 1 here. And there's no information going from robot 1 to robot 2. Robot 2 doesn't care about robot 1's position in this case. So now, our graph Laplacian here is going to wind up being d in this matrix minus our adjacency matrix here. So this is going to be winding up being 1 minus 1, 0, 0. And so now we can check, okay, well, we have our consensus equation in this form where we use the graph Laplacian, so let's see if these two match up. So we have our graph Laplacian times the negative times x, which is x1, x2, and this is going to wind up being minus x1 plus x2 and 0. And this is perfect. This matches up exactly what we have up here. x1 is going to be x2 minus x1, and x2 dot is going to be equal to 0. So this works out, and this is the small difference that allows us to derive the graph Laplacian for a directed graph in this case. Now let's solidify this idea of creating a graph Laplacian on a directed graph by looking at a cyclic graph, which is what we're going to be using in order to do cyclic pursuit later in this video. So let's consider a cyclic graph with 5 agents. For a cyclic graph, we're only going to connect each agent to another agent once. And it's going to form a cycle. Now, because we want them to chase each other, we don't want everyone to be able to measure all of their neighbors. We're going to direct this information flow. So let's say that I want robot 1 to chase robot 2. That would mean that, well, robot 2 would have to pass the information to robot 1. If I want robot 2 to chase robot 1, then I need robot 1 to pass the information to robot 2. So let's have the cycle go this way. And so we're going to have robot 1 pass information to robot 2 so that robot 2 will chase robot 1. And we'll keep doing this around. So robot 3 will measure information from robot 2. The information flow is this way. So if I'm trying to run consensus, the only neighbor that 3 cares about is 2, so it's going to drive towards 2. And we'll keep going this around. Great. So now let's form our graph Laplacian for this and run the consensus equation. So recall that the Laplacian for a directed graph is the in-degree matrix minus the adjacency matrix. So the in-degree matrix for this scenario is going to be, well, 1 has only one edge going into it, 2 only has one edge going into it, 3 has one edge, and so this is going to be a 5 by 5 identity matrix. So along the diagonal, we're going to have a bunch of 1s, and then on the off diagonals, we're going to have a lot of 0s. Whew. A 5 by 5 identity matrix. And so for our adjacency matrix, we have information going to a robot or coming from a robot, being the columns. So this is 1, 2, 3, 4, 5, or you can come from robot 1, 2, 3, 4, 5. Build out our matrix here. So there's no self loops here. No information is flowing to robot 1 from robot 1 or to robot 2 from robot 2. So the diagonal of this matrix is going to be a whole bunch of zeros. Now let's see. Is there information going to robot 1 from robot 2? No. The only information going to robot 1 is from robot 5. Is there information going to 2 from 1? Yes, and from no other sources. Is there information going to 3 from 2? Yep. And you can almost see a pattern here. And so this is our adjacency matrix. And so in order to create our graph Laplacian, we do our in-degree matrix minus our adjacency matrix. So our graph Laplacian, with which we can write down the dynamics of the consensus equation very quickly in matrix form, is going to be 1, 0, 0, 0, minus 1, minus 1, 1, 0, 0, 0. And you can see it has a very nice form here. And this is our graph Laplacian. Oh, sorry. Yes, there's a minus 1 here. Boom. This is our graph Laplacian for a 5-agent cyclic graph. Now, let's see what happens if we run consensus on this. Will they chase each other, or will consensus do what consensus does and make them slam into each other? So now that we've seen how directed graphs are represented in graph theory and how we can derive a Laplacian to show the consensus dynamics or write down the consensus dynamics quickly, let's see how a group of robots will run consensus when they have a directed cyclic graph topology. So the topology that I'm going to work with is for 7 robots, and this is shown here on the left side. And on the right is the simulation. So if we let them go, you see they drive towards each other like consensus makes them do. Then we start getting that cyclic motion, but consensus will do what it's meant to do. And these robots are going to eventually meet up on a shared position. So I originally showed a video of cyclic pursuit being done. So what is the augmentation we need to do to the consensus equation in order to make that happen? So the real problem with applying consensus to a cyclic directed graph is robots are still driving at each other. And so long as the graph is connected, these robots are going to meet at a set point. So rather than having robots aim at each other and drive towards each other, what we really want them to do is drive along the tangent line of the circle. And so what we're going to do is we're going to use our standard consensus in a way. So here we have what looks like our standard consensus. So xi dot equals something here times our consensus equation where a robot's going to move towards its neighbor. But what we want to do now is rotate this vector. So instead of driving straight towards our neighbor, we're going to drive in the direction that's tangent towards our neighbor, tangent to the circle towards our neighbor. And so this r of theta is what's called the rotation matrix. And so what this is going to do, it's shown down here, it is going to take the vector that's pointing from xi to xi plus 1, and it's going to rotate it by an angle theta. And this angle theta is going to depend on where the robots are on the circle, but if we have them equally spaced along the circle, like I showed previously, this theta is fairly easily chosen. So if they're evenly placed on a circle at time equals 0, we want their offset, this angle we're going to rotate them by, to be equal to pi over n. And then the robots should execute a circular motion. There should be no problems. We're making them drive on the tangent direction of the circle. But it looks like in the simulation here on the left, as well as the experiment on the Robotarium on the right, like this isn't working. But the theory checks out. So we have that the robots are supposed to drive towards their neighbor, and we just rotate that vector a little bit so that it is tangent to the direction of where I am on the circle. So what's going on? Well, robots are now moving with respect to a defined angular reference based on a relative distance. And this assumes that all our robots are perfectly well behaved. And in reality, if you watch the robots in experiment move, well, they don't move perfectly. If you tell them to drive on a circle perfectly, they're gonna be errors no matter what you really do. And these errors are gonna propagate. So if I'm robot 1 looking at robot 2, and robot 2 makes a mistake, well, I'm going to drive towards that mistake. And then robot 3, who's following me, is going to make the same mistake. And while we're making mistakes, while we're following mistakes that have been made, we're also making mistakes ourselves. So error in motion is going to propagate, which shows why this is looking so irregular and expanding. But even in the simulation where motion is perfect, our robots are still expanding outwards. And this is because the robots have computation time. Everything that we've done up to this point is in what we call continuous time, meaning that a calculation can be done instantaneously and data can be acquired instantaneously. And this is just not reality. So on the Robotarium, for example, data is accumulated every 30th of a second. And so what happens is, well, I'm going to drive towards my neighbor for a 30th of a second, but as soon as I drive straight for a set amount of time, I'm no longer on the circle. And then my neighbor behind me is going to drive to that position that's off the circle. And this is going to continue on, and the circle that I'm following is going to expand indefinitely. So how do we fix this? So it was a little disheartening to see the cyclic pursuit not work out in ideal terms. And the fact of the matter is that computation time and robots not moving perfectly is a fact of life, and if cyclic pursuit can't work with those things involved, then I guess it can't work. The nice thing is, though, you can make augmentations to this in order to make it actually work in reality. So to begin, let's look at what's supposed to be done ideally. So we talked about this rotation vector. So xi dot, so the way that robot I is supposed to move is, well, we take a normal consensus where we do xj minus xi, where xj is just the neighbor that you're looking next to, and we rotate that by some theta. And in the scenario we've been talking about, these are evenly spaced robots on a circle, and so in this case our theta winds up being pi over n. But so we're just rotating this vector. The thing is that robots, in order to correct this, can't measure the angle that they are relative to another robot with respect to the center of a circle. It becomes muddy. And so really what they can measure is distance. The information that's being passed in all of these rendezvous and consensus problems is positions of one another or measuring distances between one another. So let's figure out, how does this angle correspond to a distance? Well, so let's assume that these robots are supposed to move on some circle with radius little r. And so I'm going to put just two of the circles that are doing this cyclic pursuit here. And if I have n of them, the angle that's supposed to be maintained between them, this theta here, this theta ideally should be 2 pi over n. And so we can't measure this angle, but what we can do is, well, these robots can measure the distance between each other. And so I'm going to call this distance, norm is just a distance, xj minus xi desired. So this is some desired distance that I would like the robots to hold between one another. So let's blow up this triangle and let's look if we can figure out what this is supposed to be. So I've expanded this triangle. Here's the center of my circle. These are my two robots. Recall, this is the distance r because the robot is supposed to be on the radius of this circle. This is also the robot r. This angle here is 2 pi over n. And what I would like to find out is, well, what's this distance supposed to be? Right? This is our norm of xj minus xi desired. This is what should happen in ideal scenarios. So if everything worked perfectly, if robots didn't have computation time, if they didn't move irregularly every once in a while, this is the distance they would hold. And so what would this be? Well, if I bifurcate this angle, this is a right angle, I have, well, the sine of 2 pi. I've bifurcated this angle, so now it's over 2n, and this is going to equal xj minus xi, this desired distance, divided by 2, because it's half of this distance, and this is all going to be over the hypotenuse of this triangle, which is r. So now if I multiply both sides by 2r here, I get that xj minus xi desired should be 2r sine of pi over n. So this is a number that I can compute based on the radius of the circle and how many robots are doing the cyclic pursuit. And this is great. So now, where's the problem? Well, the problem is that I have this xj minus xi. And this is some actual distance, and this is not necessarily equal to xj minus xi desired. So what do we do? Well, I've erased the board a little bit, but the major result we got up to was that this is the desired distance that I would like to hold. And this is a static number with respect to the radius of the circle that I want these robots to be doing cyclic pursuit on, as well as the number of robots that are actually performing the pursuit. And what we said at the end was, well, the actual distance, because of computation time, sometimes expands, sometimes shrinks, because robots are driving outside or inside of the circle and not perfectly on that circumference. So what we can do to rectify this is we can use a proportional controller. And so if you have done control theory, you can even extend this to a proportional integral derivative controller, but in the interest of simplicity, we're going to have a proportional controller. If you haven't heard of a proportional controller, I'll give you some intuition about how this actually works. But the main idea is this. So for a proportional controller, what we're going to do is we're going to have some positive gain, which I'm going to call KR, and then I'm going to find out what the difference is between what I'm supposed to be doing and what I'm actually doing. So I have the distance that I'm supposed to maintain as robot I minus the distance that I'm actually maintaining. So this is, again, this number that I've computed, and this is what I'm measuring from the robot ahead of me. If maybe he's getting too far ahead, maybe they're getting too close. And so this can be this is our proportional correction factor. And so what we can do with this now is, well, recall at the very beginning how we're doing cyclic pursuit is we are taking this idea of doing rendezvous, and instead of driving straight at our neighbor, we are rotating by some said angle. And the problem is that this said angle, if a robot is slightly off, is going to be wrong. And it's actually going to push us further away or further into the circle. And so what we can do now, using this proportional controller, is we can say, okay, well, this angle is going to be pi over n, so what it's supposed to be, plus this proportional term. And so, great, what this is doing is, well, if there's no difference between the distance that we're holding and what we're supposed to be doing, this term goes to 0, and so we just do the nominal case, which we have shown would work if we didn't have computation time and other things that cause error. Now, if we go outside the circle, so our robots have taken too long and we followed that tangent line a little too long, and so we've actually expanded where we're supposed to be on the circle, this distance is going to be larger than our nominal distance, which makes this term in the bracket, in the parentheses here, negative, times KR, which is a positive number, a positive gain. So this positive number times a negative number is a negative number. So what we're going to do is rotate by a smaller angle. And what that's going to do is actually push us back towards the circle, inwards towards the circle, because we're outside. Similarly, if for some reason we've driven inside the circle, this distance is going to be smaller than our nominal distance. And so this will be a positive number times a positive number. We're going to actually rotate our angle slightly more out and drive towards the circle now. So this is going to be our way of dealing with the fact that, hey, this isn't going to behave perfectly. Our robots aren't going to move so that this distance is perfect all the time. So let's correct that here and add it to the nominal factor. So this here is our correction to make this work in reality. And rather than just telling you it'll work, let's see this happen in simulation and on the Robotarium. So here's a simulation and an experiment on the Robotarium using cyclic pursuit, so our standard idea of consensus, with this angular offset. So we're rotating our consensus vector using our directed cyclic graph and rotating it by this angular offset that has a proportional correction to deal with the fact that robots aren't going to always move perfectly and there are computation time. So our simulation here looks wonderful. Our experiment, on the other hand, still has some issues, and this is because, again, robots don't move perfectly. There's no real way to completely reject this. We could take time to tune the proportional gain. We could potentially use a proportional integral derivative controller to make this perform better, but this is more of a proof of concept that by applying this augmentation, we can perform cyclic pursuit in reality and deal with the fact that there are complications when you're actually applying this to real robots. With us completing cyclic pursuit and that augmentation of the consensus equation, let's now shift gears and look at a different way of applying the consensus equation to assemble a formation. So our goal here is to take some robots at some initial time in some initial formation, and by t equals infinity, what I'd like them to do is I would like them to achieve some geometric formation that I've specified beforehand. So in this case, I have taken them from this position. I would like them on their own using only local information and some version of the consensus equation to wind up in some geometric formation that I have specified beforehand. In this case, a diamond. So to reiterate, our goal is to have the robots move from some set initial position, which I'm going to call here x naught, to some final position y. And to start off, let's do this through position control. So I'm going to say, well, robot 1, I'd like you to move to position 1. Robot 2, I'd like you to move to position 2. Robot 3 to position 3, and robot 4 to position 4. And that's great. This does achieve a formation, but we're not doing formation control. We're not even doing network control. There's no information passing between robots. I'm simply telling them to go to certain positions, which they can't necessarily even measure. And the fact that is that because they're in these positions, this formation happens to fall out. And so the goal here is still the same, that I'd like them to move to a set of positions such that their final inter-robot distance, so what I really care about is the distances between all of these robots here in the final configuration. So mathematically writing this down, my goal is I would like all of my robots' positions, x, to wind up in some final configuration that I have specified, y. But now let's have a quick thought exercise. So what if 4 has a malfunction? So robot 4, instead of winding up here, actually winds up over here, translated by some vector beta. Similarly, robot 3 goes through the exact same malfunction because we're that lucky, and robot 3 is now moved by the same vector beta, and robot 2, and robot 1. Well, it turns out that this new formation, that's y plus beta, is perfectly fine for what I care about. I don't care where the robots are in space. What I care about is their inter-robot distance. And so long as this distance is preserved, my formation can be over here at y, or it can be over here, y plus beta. So my goal really is to have my initial positions, or the positions of all of my robots xi, go to some final position yi, translated by some random vector beta. We don't care. So the position and the formation information is given by a designer, by an engineer, by a control theorist, by giving it this yi, but we don't care in space where it is. And so our approach is we want to have the robots achieve the same error from the designed final position formation. So what we'd like them to do is, well, I want them to achieve this position formation, but I don't care where it is, as long as they all have the same error, beta. And we know how to make robots agree on something. If we wanted robots to agree on a position to meet up, simply by passing information to each other through a network, we would run the consensus equation. So now let's run the consensus equation on the error, because I want all of the robots' errors to be the same. So the error for each robot I is going to be where I want them to be, yi, this is designed by us, minus where they are, xi. So we write down our standard consensus equation. Ei dot is going to equal the sum over the neighborhood of I of ej minus ei. And if I take this limit to infinity and I make these run forever, what's going to happen to this error is, well, it's going to drive to 0. And what that means is that the error of j is going to equal the error of I for every j in the robot's neighborhood. And so that means that every error of every robot is going to be the same, and I'm going to call that beta, where beta is where the robots wind up minus where they were supposed to be. And so this is great. We have a different application of the consensus equation to show that formation control can be achieved if you put consensus on the error signal, which means that it will work. And, there's a big question here, and it's, so what? We can't measure y. We can't drive to these locations, and nothing here tells us x dot. There's nothing here that tells us how we should actually move our robots in order to achieve formation control. So let's do that. Let's now take our consensus, where we said if we run consensus on the error signals, what we can show is that formation can be achieved, and let's figure out how we should move our robots so that this consensus works in the way that we want it to. So first I'm going to rearrange the error signal, the error equation. So instead of having my error equal where I want to go minus where my robot is, I'm now going to say, well, my robot is going to be where I'm supposed to be minus how much error I have from where I'm supposed to be. We care about the motion of this robot, so we're going to have the time derivative of each one of these variables. And the nice thing here is, well, y of I is a static formation that I have chosen ahead of time. In the original example, I said I want a diamond, so these positions are fixed in time. Thus, the time derivative of this is going to be 0. The other nice thing is, well, I know the dynamics of my error because I looked at them to prove that the formation control will work out. So I'm just going to substitute this equation into here, and I'm also going to substitute in EJ and EI with their respective yi minus xi and yj minus xj. And so what we wind up with is, well, the dynamics of robot I are going to equal the negative sign sticks around, and then we have our standard consensus equation where we have, well, the error of j minus the error of I. I'm going to rearrange this to stick x's together and stick y's together, and what should pop out is kind of nice. So we have here this first part of our equation. This is standard consensus. And now we have some difference between neighboring robots. And when I originally said, okay, well, I'm specifying positions that I can't measure, I can definitely specify distances that are to be held between sequential robots. And so if I rewrite this, I get my lovely formation controller that makes everything work out here. And this turns out to just be, well, this is standard consensus minus some desired final interagent distance. And this is something that we define ahead of time. So this gamma ij is the set of distances between pairs of robots that will give me the formation that I'm looking for. So before we get too excited, let's talk about some of the assumptions that are lying under the hood of this equation. We have our standard consensus equation assumption. So something that we haven't talked about, but our standard consensus equation, just this part, assumes that, well, xi can see xj and measure it from infinitely far away. There's nothing here that says that a robot can't see another robot. I guess you can technically say it's specified in this neighborhood, but if you just assume that these two are always connected, then there's infinite sensor distance here. Robots don't take up physical space. We talked about this previously, but if you run consensus in simulation, well, they're going to wind up on the same spot and slam into each other. Our robot actuators are not limited. So if xi minus xj is huge, let's say it's 1,000,000 miles or 1,000,000 meters, well, then the xi minus xj being 1,000,000 is going to mean that xi has to move at 1,000,000 meters per second, which isn't feasible. And finally, robots don't have any motion constraints. And we've talked about this when we did the video on the Robotarium. We can do transformations, but for a general robot system, this is assuming that a robot can move in any direction instantaneously. We now have some additional assumptions associated with this offset for us to do formation control. Our offsets have to be given to the robots a priori. They need to know ahead of time, well, how far am I supposed to be from Bob over there? And all robots need to agree on a global coordinate frame because these distances are associated with an orientation. I need to be a certain X distance and Y distance away from Bob. And if Bob and I don't agree on which way is X and which way is Y, then it's not going to work. And finally, this is a gamma ij, so robot I needs to know that it's looking at robot J. So there's some knowledge of robot identity here. So I need to know that I need to stay a set distance from Bob. I also need to know that I'm looking at Bob to stay a set distance away from them. And so just to wrap up and show, this actually works. So here's a rigid formation that we have given for these robots to follow using this consensus equation with offsets. And it's great. Everything works, and all that's being done here is that we have our normal consensus equation, and we've just added the offsets, which can be seen within these videos by where these robots settle. These are the offsets between robots that know of each other and who each other are, so that they can hold these rigid formations. This brings us to the end of our introduction to formation control and cyclic pursuit. In today's video, we discussed how we can massage the consensus equation to make it do cool things like have robots chase each other in a circle or hold specified geometric formations. But there are caveats here. There's an underlying assumption that all robots agree on a coordinate frame. They all agree on which way is north, south, east, west. And in general, that may not be possible with the robots that we're using. So in future episodes, we'll drop those assumptions. We'll try to do formation control without having to agree on a coordinate frame. And we'll do some other applications as well. But we'll leave those details for a future video. And I hope to see you there.